Hello and welcome to problem 17 in my Calculus 3 or Multivariable Calculus problem solving series. In this video, we're going to look at how to solve triple integrals for a volume enclosed by two surfaces. So in the previous video, we looked at triple integrals over a volume that was enclosed by a box or a rectangular prism. But in today's video, we're going to look at more organic shapes of volumes where the volume that we're integrating is between two surfaces. So let's say that you have a function f of x, comma y, comma z, and this function represents the density at every point in 3D space. And we want to find the triple integral of f of x, comma y, comma z over the region B, which is the volume between these two surfaces. So we have surface 1, which is z1, and the second surface is z2, and these are both functions of x and y. And to do this, to find this triple integral, we're going to take the triple integral of f dz dy dx. So dz dy dx is dv. And our bounds for the integral are going to be from z1 to z2, or this distance, from y1 to y2, this distance, and from x1 to x2. So y1 and y2 is the function, is this curve on the xy plane, and it's sort of like if you had a light on top, then this would be the shadow of the surface in the region that you're integrating. And then x1 and x2 are constants, and that's because on your triple integral, the outside integral always has constants. And when we find this triple integral, it represents the mass of this volume. So let's go ahead and look at an example of how to solve triple integrals. So here we have the function f of x, comma y, comma z, which is 2x. And the region in which, or the volume in which we're going to be integrating is the volume from this plane, 2x plus 3y plus z equals 6, all the way to the xy plane, or the plane z equals 0. So it's going to be like this triangular prism that's enclosed in this corner. And this is going to be the view of the xy plane. So first step is to define our bounds for the integral. Our z bounds are going to be from the plane z equals 0 to the plane z equals 6 minus 2x minus 3y. Our bounds on x are going to be from 0 to 3, while our bounds on y are going to be from the line y equals 0 to y equals minus 2 over 3x plus 2, or this line. So we can use this graph to help us look at the bounds on y. And so now that we have the bounds on x, y, and z, we can define our triple integral like this. So on the outside, we have x, because x has the constants. On the second integral is going to be integrating for y from 0 to minus 2 over 3x plus 2. And on the third integral, we're going to be integrating from 0 to 6 minus 2x minus 3y. And the function that we're integrating, f, is going to be 2x. And you might notice that as you go deeper and deeper into the triple integral, you're increasing the number of variables. So this integral doesn't have any variables. This one has only x, and this one has x and y. So that's how you order them. So then we can start solving this triple integral like any other. And we get 2x times z from 0 to 6 minus 2x minus 3y. And then we get this double integral of 12x minus 4x squared minus 6xy. Then we solve this integral, and we have to evaluate it from 0 to minus 2 over 3x plus 2. And finally, we're left with the single integral. And we find out that it's 9. So this can represent the mass of the triangular prism that was enclosed in this area.